So now we've got the 82 grams attached to the bottom of the pendulum, using DVD cases for my heart. Wedged it on just so I can do a quick release with one hand. Not the most ideal, but if we just go 1, 2, 3, go. So 1, 2, 3, go, and then that will run for an amount of time. We give it a potential and gravity, and that system has that amount of energy in it, and this will go back and forth until it winds down to friction and comes to a stop. Obviously you'll have to, I have timed this, but obviously I can't film it and time it at the same time. But roughly, when I was timing this one, it's around about the 40-second mark, so there we go, it's stopped. We'll try that again. So again, we've got it set up, we're at that 4 height, 4 boxes. We'll do 1, 2, 3, go. And again, it will swing back and forth. Like I say, it's worth timing. Get your stopwatches out. But again, roughly, I get very consistent, sort of around about the 40-second mark. Sometimes a little bit under, sometimes a little bit over by a second maybe. So that's 82 grams at 1 height displacement, and that's the run time, which is roughly about 40 seconds. And we'll do one more. So again, another one. We'll go 1, 2, 3, and then we'll go 1, 2, 3, go. And like I say, this ideally you need to get, you can judge the video on the run time of the video, or you can just stopwatch from when I say go to obviously when it runs out of energy to friction. And like I say, I'm getting roughly about, like I say, the 40-second mark. It's winding down, and obviously the friction will be the same, relatively the same for both. So, and there we go. We'll do one more just to be sure. Right, and again, so we'll do the 1, 2, 3, go. 1, 2, 3, go. So again, the time, when we do the half mass at 4 displacements, the amount of time it's going to fall in gravity is the same as this does. So if there's more energy, the time in gravity, it's not a time dependent force, obviously, because the time in falling would be the same. So it's winding down. So basically you've got a time from, the 1, 2, 3 release to the point where obviously it comes to a complete rest. And that gives us the amount of energy in the system. Maybe do one more. So again, we'll do one more. 1, 2, 3, go. So like I say, I'm just using DVD boxes because I'm just thinking they're pretty uniform. So we've got 4 there, so 16 we'll need, and obviously half the mass. Obviously there's a little bit of length of lever below the weight, so ideally when we go up to 16 it's probably a little bit under in height, because we'd have to 4 times that distance as well. But just to make the point, as a quick demonstration, I don't want to get too involved in it measuring wise, but it'll show what we need to show. So again, it's come to a stop. So now we've got, this is going to be as half mass. So this is obviously small ball bearings, On the other one we had 4 magnets. Obviously on this one we've only got half of that. We've got 2 on each side, and that weighs 42. So that's a little bit. This is a little bit over, because what did we have? 82. So was it 82? So ideally we did 84, 42, or 82, 41. But so it's a gram over. So it's pretty much half the weight, like I say. But the distance wise, obviously, you maybe need to go a little bit higher than I am doing. But we'll just test it out. Alright, so now we've got that 42 grams in the same position as before, as the hot, double mass. We've now raised it, so we had 4 DVD boxes, we've now got 16. So 4 times the height, 4 times the displacement in gravity. So it's going to fall in gravity for the same amount of time. It's going to go twice as fast, so it will have equal momentum as the 2 mass from 1 displacement. So the momentum, that the initial angular momentum is equal. The velocity is going to be double. The time in gravity is going to be the same. So if the momentums were equal and the time in gravity is the same, then you could say that the energy that this is going to have is going to be equal to the 2 mass, and therefore we should get the same run time. But if we go look in terms of energy, obviously to get this going twice the speed, we've got to put more energy into the system. And if we put more energy into this system, we should expect to see more energy out, more in, more out. It's going to conserve the energy, and therefore we should get a longer run time. But if all is equal in terms of momentum and gravity being a time-dependent force, then we should see an equal run time, which it was roughly about 40 seconds, wasn't it? So that's what we're looking for, a run time of about 40 seconds for everything to be equal. But if this has more energy, obviously that's going to run for a longer time. So we can test it out, obviously. So same as before, obviously, because I'm filming and I can't, I ain't got 10 pair hands. It's just going to be the same. It's wedged onto there. I'll just quickly move that. It'll release it and it'll run for a time. So again, we'll do the 1, 2, 3 and release. 1, 2, 3, go. So again, from the 1, 2, 3 go, start your watches or your stopwatches, or the ones on your phone, which is what I use mainly. But we can see that obviously it's running away now. It's going. It's winding down to friction, and eventually it will come to a stop. But what we're interested in is how long it takes for that to happen. Because if everything's equal here, say time and gravity, same. Momentum, the same. Energy, not the same. And it's still going, so we've got to wait till it comes to a stop. I think that's pretty much there. So we shall try that again. So we'll go again. Like I say, this might not be the most accurate in terms of height measurements and just measuring, but it's just an easy way for me to do it, with one hand. Perhaps this just does need to be a little bit higher. But when from this setup and just measuring the time, it's roughly running for about 1 minute 10-second mark, where the other one was 40 seconds. So clearly there's more energy in the system. Sorry, I didn't do the 1, 2, 3 go there, did I? But yeah, as we let this one go and fall in gravity by the same amount of time, with the same initial momentum, angular momentum due to its velocity that it gains. But like I say, the energy input, we've got to raise this to that height, and that takes an amount of energy. I suppose it's like, compressing a spring in a way. You're lifting it up, you're compressing the spring. When you let it go, you get that energy back. And clearly this is running, what did we say, roughly about 1 minute 10 seconds. The other one was 40, so what's that, 30 seconds long there? Not quite double, but a lot more. So again, we'll go again. I'll give you a 1, 2, 3 go this time. I say, when I'm wedging it, obviously sometimes I'm probably doing it a little bit higher, a little bit lower, so we're not going to be dead consistent, but it's just to get the point across. So 1, 2, 3, go. And like I say, if we go with momentum and momentum rules, then they are of equal momentum. And if momentum was a measure of energy, then we're putting the same energy into the system, and therefore we should get the same run time. If we say gravity is a time-dependent force, we're also letting them drop for the same amount of time in gravity, and therefore they would have the same energy, and they would again get the same run time. But that's not what's happening. That's not what's occurring, basically. I say we're having to put more energy in by raising it to that height, and we get that back. We put that into the system and we get it back. It's still going. So again, we're looking until it comes to a complete rest, and there we go. Right, so we'll do one more. I say there are 16 there. If you want to count them, let's say we use 4 and then we use 16. So it's probably not the best, measurement wise. Like I say, I could faff about trying to measure it, but this just gives me a ballpark figure, and obviously I can really sit with one hand and film it at the same time, where if I was holding a tape measure up and all that, it'd be really difficult. So we'll go again. I'll give you a 1, 2, 3, and I'm just looking at the time here, so we'll get to dead on 0. 1, 2, 3, go. And then we can see how long it runs for. So like I say, same momentum, so it's half the mass going twice the velocity, falling for the same time in gravity. All we've done is displaced it more in gravity, and it's clearly more energetic. Because you've got to explain, if we're saying gravity, if it's in gravity at the same time, it should be the same energy. If momentum was energy, it should be the same energy. But if we go with MGH, we've got the mass, gravity, and we've got the height displacement, and from that you can work out the energy. And in this case, to get this one up to the 4 height thing, we've basically added twice as much energy. Alright, we'll do one more, and then I might just go back to the 2 mass at the 1 distance, just so we can see the difference. So again, 1, 2, 3, go. So MGH works basically. MGT, there is no time in this really to figure it out, because the time it takes to raise it is irrelevant. So I could take a second, I could take a month, I could take a year. You know, the high to raise it to, once I let it go from that high, that's the energy I'm getting back. And again, it's falling for the same time, regardless of how far we displace it, it's falling for the same amount of time. That initial sweep in will be the same amount of time for both. Yeah, this one is running for a lot longer before it winds down to friction. And it's still going, so we're just looking to when it comes to a complete halt, and that'll be his time. And like I say, I roughly time that about 1 minute 10, but maybe this needs to go, like I say, maybe a little bit higher. Alright, so back again with the 2 masts now, using 4, wedged it on and let it go. 1, 2, 3, go. So again, these would be equal momentum, equal full time in gravity, but different energies due to MGH. So again, from the 1, 2, 3 go to the moment it comes to a standstill, and that's the time we're looking for. Alright, so one last one. So again, at the 4, this is the double mass. So 1, 2, 3, go. So it was pretty consistent results actually. So when I was timing this, it was roughly about the 40-second mark. Slowing down, and eventually it will come to a stop. And there we go, it ceased to be. Right, I'm back to this, but having measured it now with a tape measure, when it's at the 4 heights, measuring to the centre of the mass from the table, it's roughly about 7 centimetres off the table. This I've just measured, and it's actually quite a bit under. It's about 25, so we'd have to add a few more boxes really ideally to get that to the 28, so I might just do that, and then obviously rerun it and see what we got. Right, so we're back. I've added a little bit more. I think I've added 2 more now, and that's bringing it, when I measure it from the centre to the table, that's this one was roughly 7 centimetres. This is now 4 times that, which is 28 centimetres, almost to the dead centre. So this is probably more accurate than before, but I don't think it's going to make a huge difference to run time, maybe a second or 2. It's only a little bit higher. So again, we'll do the 1, 2, 3, go. 1, 2, 3, go. And again, we just, I think when I timed it, roughly about 1:10, 1 minute 10 seconds, as opposed to the other one running for 40 seconds. So clearly more energetic, more energy in, more energy out. Because like I say, even though they are equal in terms of momentum, we have to give this one more energy for it to have the same momentum as the 2 mass. It takes more input. Still going. And there we go. It's come to a stop. So there we go. Right, I just wanted to have this bit in at the end because through the editing process, obviously I was looking at the times, and I think for the half mass at twice the velocity, I was saying around 1:10, but it was roughly about 1 minute and I think 3 seconds or 5 seconds, something like that. So I was saying 1:10. I don't know, I messed that up, but like I say, as I was looking through and editing, I was just checking the time. So yeah, we were looking for the 2 mass. It was quite consistent. I was getting that one right, I think, around 40 seconds. And the 1 mass at twice the velocity was around 1 minute 3 seconds on average. So somebody who's obviously a lot more competent on the mathematical side of things might see what the relationship is here. I'm not entirely sure, but clearly, you know, there's twice the energy going in and there's considerably, you know, more run time. Like I say, same momentum, same time and gravity, but clearly, you know, there is a different amount of energy in the system.